Hello dear students, today we are going to study optical isomerism in coordination compounds. I hope all of you know what is the meaning of optical isomerism. It's due to the fact that when a plane polar light is passed through an optical active compound, this compound rotates the plane of the polar light either clockwise or anti-clockwise. So, due to this phenomena, the compound is called optically active, and such kind of optically active compound is found to exhibit optical isomerism. The main condition for the optical isomerism is just like in the organic compounds. In the organic compounds also, you know, the presence of optical activity in a compound is due to one fact. What was the fact? The fact is absence of any element of symmetry. That means the molecule should not have any element of symmetry. I hope it is clear. Now, we are going to apply the same information of the optical isomerism in coordination complexes. Just like in the organic compounds, any optical active compound is found to exist in two forms. One is D form and one is L form. D stands for dextrorotatory and L stands for levorotatory. Now, what is the meaning of dextrorotatory? When the plane of polar light is rotated towards clockwise direction, the compound is dextro, and the one it is rotated by towards anti-clockwise direction, it is called as levorotatory complex. And D and L, both complexes or both optical active forms are mirror images of each other. They are such mirror images which are non-superimposable. So such non-superimposable mirror images are also known as enantiomers. Alright, so all the same basic informations are to be applied in the optical isomerism and coordination compounds. Dear students, we'll study optical isomerism in two kind of complexes. One is coordination number 4 complexes, and the next one will be coordination number 6 complexes. When it comes to the CN4 complexes, so CN4 complexes can be of two types: square planar complexes and tetrahedral complexes. Now, in case of a square planar complexes, the metal and the ligand, they lie in the same plane. Since they lie in the same plane, so due to the presence of plane of symmetry, plane or excess of symmetry, such kind of CN4 complexes are optically inactive. Optically inactive means they do not show the phenomena of optical isomerism. Now, when it comes to the tetrahedral complexes, as in the organic compounds, we all know tetrahedral geometry, organic compounds which possess tetrahedral geometry, they show optical isomerism. So same here should be applied in the coordination complexes, especially the coordination complex of the type M, A, B, C, D, N plus minus. Such kind of complex, the central metal atom or ion possesses the chirality. What is the meaning of chirality? When, like in case of organic compounds, when the carbon is attached with 4 different groups, this carbon is said to be chiral carbon. So same thing as here. This central metal atom or ion possesses chirality because it is attached with all 4 different ligands. So on that basis, such complexes do not possess any element of symmetry. So these kind of complexes should show optical isomerism. Alright? And they are found to possess. But due to their labile nature, these kind of complexes could not be resolved successfully. So we can say that CN4 complexes, square planar, are optically inactive. tetrahedral MABCD type of complexes are optically active, but they could not be resolved due to the labile nature of these complexes. So it's not very fruitful, or we can say it's not very common in CN4 complexes, this optical isomerism. Now coming on to the CN6 complexes. So dear students, CN6 complexes, we have octahedral complexes containing only monodentate ligand. So when we say monodentate ligand, so here if I write some of the complexes like M, A2, B2, C2, M, A2, B2, CD, M, A2, B, C, D, E, and M, A, B, C, D, E, F. All such kind of complexes, they do not possess any element of symmetry. So they all are optically active compounds. But we do not study them under the heading of optical isomerism so commonly. It's due to the fact that due to improper conditions in resolution of these compounds, that means these compounds cannot be resolved properly under normal experimental conditions. So due to this fact, octahedral complexes which contain only monodentate ligands, though they possess optical activity, but their study is not very common. Now when it comes to the octahedral complexes containing one or more symmetrical bidentate ligand, what is the meaning of symmetrical bidentate ligand? In the previous video I have explained about that, like AA type. And the best example for this I taught you oxalato, where both the donor atoms are same. That's the reason I represent it using AA type. Both the donor atoms of the bidentate ligand are same. Such kind of ligands, they are chelating ligands because it gives rise to chelation. I hope you understand the meaning of chelation. Chelating ligands are those ligands which are, when bonded with a central metal atom or ion, they give rise to a ring-like structure. Alright. So here we comfortably see the presence of optical isomerism, as well as such kind of complexes can easily be resolved. So it's very comfortable to study optical isomerism in octahedral compounds, those compounds which contain one or more symmetrical bidentate ligands. So let us see some of them here. The first one in this category is MAA whole thrice. That means 3 similar bidentate ligands. So see, look at we can have, it's this kind of geometry where 3 bidentate ligands are oriented that way. Now this complex is the exact mirror image of the first one. So this is the D form of the complex and this is L form of the complex. Since both are non-superimposable mirror images, so we can say that they are enantiomers of each other. I hope it is clear. Now coming on to the next one, the second example in this category will be MAA whole twice A2. Here we have 2 similar symmetrical bidentate ligand along with 2 similar monodentate ligand. So here the complex can have this kind of geometry. So where 2 symmetrical bidentate ligands are oriented that way and 2 similar monodentate ligands, they occupy the square plane. Now this is the D form of the complex and this is the L form of the complex. So L form and D form both are mirror images of each other. They are non-superimposable mirror images. So they are enantiomers of each other. Alright, and both are optically active. Now we can have one more kind of orientation of the ligands around the central metal atom in the octahedron. So this is the third way where 2 symmetrical bidentate ligands can occupy the different places in octahedral geometry. So this kind of complex, it possesses a plane of symmetry. So due to the presence of an element of symmetry, this is not an optically active form of the complex. This particular form of the complex is the mesoform. Mesoform. I hope it is clear. So this was the example about MAA whole twice A2. We can summarize it here that optical isomerism we study in CN4 complexes and CN6 complexes. CN4 two kind of complexes, square planar tetrahedral. Square planar due to the presence of plane of symmetry. It do not show optical isomerism. Tetrahedral complexes they show, but of the which kind of complexes, like MABCD kind of complexes, but due to their labile nature, optical isomerism is not common in tetrahedral complexes as well. When it comes to the CN6 complexes, so we can have two kind of complexes, the one which containing only monodentate ligands and the second containing one or more symmetrical bidentate ligand. When it comes to the monodentate ligands, so here possibility is there, but due to poor resolution experimental conditions, it's not very common or it's not very comfortable to study in such kind of complexes. But due to easy resolution experimental conditions, the kind of complexes CN6 containing one or more symmetrical bidentate ligands, it's very easy to resolve these compounds as well as to study their optical isomerism.